Hello everyone, and welcome back. In this video, we'll continue building our ball balancing PID controller using Verilog. The screen you're seeing now shows the progress that we made in the last video, where we designed the circuitry responsible for taking the sensor measurements and filtering out the noise from those readings. That portion from the last video corresponds to the pink section in the full PID block diagram. In this video, we'll be implementing the PWM controller module, shown here in the yellow section of the block diagram. After building the module, we'll create a top-level test module that lets us control the servo in real time, allowing us to see the PWM output in action and prove beyond doubt that our Verilog design works exactly as intended. What you're seeing on screen right now is the final result of this effort, the PWM controller driving a servo and responding to our switch and button inputs in real time. Before we can make the PWM module, we must first discuss the datasheet for the servo. The datasheet for the servo is as follows. We control the angle of the servo by applying a pulse between 0.5 milliseconds and 2.5 milliseconds. To get it in the smallest angle, we apply a 0.5 millisecond pulse. To get it in the center, we apply a 1.5 millisecond pulse. And finally, to get it into its maximum position, we apply a 2.5 millisecond pulse. Also note that according to the datasheet, each pulse cannot repeat at a frequency that is faster than 3 milliseconds. So now that we know how to drive the servo, we can begin designing the PWM controller. This is the PWM controller module. To start, let's go over the ports that it has. It has an input RFT, which is a signed integer representing the response value produced by the PID controller. It also has a start input pulse that triggers the generation of a new output. The output, PWM out, is the signal that drives the servo motor. And finally, the done output indicates when the PWM pulse has finished generating. So in summary, the PWM controller takes an RFT and generates an output pulse through its PWM out port. The length of this pulse is directly proportional to the magnitude of RFT, meaning that larger values of RFT produce longer pulses and that smaller values of RFT produce shorter pulses. For example, when RFT is equal to 0, the pulse is 1.55 milliseconds long. When RFT is equal to 30,000, the pulse is 1.85 milliseconds long. When RFT is equal to 60,000, the pulse is 2.15 milliseconds long. When the pulse is equal to 65,000, the pulse reaches 2.20 milliseconds long. So you can express this proportional relationship with the following equation, where PWM out length in milliseconds is equal to 1.55 milliseconds plus RFT all over 100,000 in milliseconds. Also note that the PWM controller should clamp its output pulses between 0.9 milliseconds and 2.2 milliseconds. Doing this prevents the servo from rotating too far. For this reason, the system treats any RFT value less than negative 65,000 as being equal to negative 65,000, and any value greater than 65,000 as being equal to 65,000. Before we go over the code and simulation, there's one important detail I need to emphasize. In the equation, you might be wondering why I used 1.55 instead of 1.5 for the center position. The reason is purely mechanical. When I applied a 1.5 millisecond pulse to get the servo into its true center position, the gear teeth were so coarse that even though the servo itself was centered, there was no way to fit the arm onto the gear in a perfectly horizontal orientation. Here's a video showing this, where I applied a 1.5 millisecond pulse and put the arm on as straight as possible, and you can clearly see that the arm ends up slightly tilted, even though the servo is centered internally. As you can clearly see, the arm is slightly off from being level. If I would have ignored this, it would have caused problems later on. To fix it, I sent in a 1.55 millisecond pulse after fitting the arm as closely as possible on the 1.50 millisecond position. Here's a video showing that. Since the servo was perfectly straight at the 1.55 millisecond position, it made more sense to use that as the center rather than using the slightly crooked 1.50 millisecond position. Using 1.55 millisecond or a similar value as the center is perfectly fine. We only need about 180 degrees of smooth motion, with the horizontal position sitting right in the middle of that range. The following figure illustrates this principle. The left-hand side shows the ideal situation where the servo center position would have been perfectly aligned at 1.50 milliseconds, corresponding to 135 degrees. The right-hand side shows the actual calibrated setup, where the center occurred at 1.55 milliseconds, around 142 degrees. Now that we've discussed the behavior of the PWM controller, we can finally take a look at the actual code. So this right here is the complete PWM module, and believe it or not, it's only about 30 lines long. It's surprisingly simple, especially considering how much functionality it provides. But here's something I want to emphasize. The hardest part about designing digital systems in Verilog isn't writing the code. It's figuring out what hardware you actually want to build in the first place. That's why we spent so much time defining the hardware-level behavior of the PWM controller. We defined clearly how it should behave for all cases of RFT before even touching a single line of code. By understanding exactly what the circuit needs to accomplish, the Verilog implementation becomes extremely straightforward. So, to begin explaining the code, we must start by reiterating that it implements this exact behavior. In hardware though, we don't measure time in milliseconds, we measure it in clock cycles. Since we're running on a 100 MHz clock, 1 millisecond equals 100,000 clock counts. So if we multiply both sides of the equation by 100,000, we can express it in terms of hardware clock counts instead of in milliseconds. From this, we can conclude that we simply need to toggle the PWM output after 155,000 plus RFT clock cycles have passed. So looking back at our code, the number of clock cycles we need to wait before toggling the output is stored in the compare value register, which is declared on line 7 and initialized to 0. Initializing it directly in the declaration is cleaner and avoids needing an initial begin block. Before we can generate the PWM pulse, we must first calculate and clamp the compare value. This all happens in the first half of the always block. On each start pulse, the 3 if statements from lines 12 through 21 run in order, one after another. The first if statement detects the start pulse and sets the count register to a specific value so that only the second if statement on lines 13 through 16 will execute on the very next clock cycle. The second if statement computes the compare value using the exact formula we derived earlier. It also sets the count register to another specific value that ensures that only this third if statement spanning lines 17 through 21 will run on the next clock cycle. The third if statement clamps the compare value register so that it remains within a safe range for the servo, and finally sets the count register to 0. Then, the second half of the always block executes. Since the count register is now 0, line 22 executes once to set the output high. Additionally, the if statement on line 23 begins to continuously execute, resulting in the count register being incremented continuously. Only when the count register reaches compare value does line 24 drive the output low. After the count register reaches 500,000, none of the 6 if statements execute anymore until a new start pulse resets the entire thing. Also note that right before it stops counting, the done pulse is generated on lines 27 through 30. The done pulse is generated on the falling edge, but it could have very well have been done using the positive edge. From my experience, there is no performance difference in how you generate the done pulses, but if you ever run into problems, consider trying it both ways to see if one works better. So now we have successfully derived the code for the PWM controller. But before we move on to explain the top-level test module, where we systematically verify the PWM module performance in real time, it's important that I clarify that there's 3 parameters that can change in my setup versus yours. To start, the constant on line 14 corresponds to the pulse length applied that is used as your center position. For me, I used a 1.55 millisecond pulse as my center, so this value was 155,000 for me. Then, the 2 constants in lines 18 through 19 are just 65,000 less or greater than the constant on line 14. Now let's take a look at how we can test this module by putting it inside of a top-level design built specifically for real-time debugging of the PWM controller. So this here is the block diagram of the test module we'll be using. It starts with the button debouncer, which generates a clean, stable pulse every time we press a button. That pulse then feeds into a signed multiplier, where we multiply 3 by a signed 16-bit number coming in from the switches. In this circuit, all 16 switches are treated as one signed 16-bit integer. The multiplier outputs a signed 16-point value called test response. Since the PWM controller was designed only to receive signed integers for the response, we feed it only the integer portion of the multiplier's product. For debugging purposes, I also bring out the compare value signal as an output. Normally, this would stay internal, but exposing it here lets us see exactly what the PWM module is using to determine the pulse width. Also, while not shown, there is also display circuitry that lets me switch between the signed 16-bit integer coming from the switches, the integer portion of the test response from the multiplier, and the compare value itself. The beauty of this setup is that we can see compare value update in real time and immediately see how the PWM output responds. We can also see how the input portion of the multiplier's fixed point product gets added to the constant 155,000 to form the compare value used by the PWM controller. Now that we understand the test setup, let's look at how the PWM controller behaves on real hardware. Alright, so this is our test setup. The way I have it, if we press the right button, we update the compare value by triggering all of the calculations to happen. If we press the middle button, we show the test response on the 7 segments, so we show the output of the multiplier. If we press the left button, we show the compare value on the 7 segments. And if we don't press any of these two buttons, the value of the switches will be on the 7 segments. So let's say we want to do RFT equals 0. Well, to get RFT equals 0, what we need to do is we just need to set the switches to 0, because 0 times 3 will give us a product of 0. Then 0 plus 155,000 is 155,000. So, which will then give us this pulse here. So let's do that. Okay, good. Now let's view the compare value. So the compare value is 155,000, and it's dead straight position, which is good. Now let's do positive 30,000. Well, to get positive 30,000, we need to input 10,000 there, because 10,000 times 3 is 30,000. 30,000 plus 155,000 is 185,000, which will give us that. So let's do that real quick. So I'm going to input 10,000. So this is 10,000 being inputted. So I'm going to press the button. So it correctly emulated that position. And let's look at compare value. So yeah, this is the value of the switches. That's the output of the multiplier. And it adds the output of the multiplier to 155,000 to give us that value, which is good. Now let's do a big value. Let's make it be a big unsigned value. So it's 26,000. Well, 26,000 times 3 gives us that. Then that added, it's very big, so it gets clamped. Now let's do the negative case where we want to add negative 10,000. So we need to change the input to be negative 10,000. So it's negative 10,000. If I press that button. So negative 10,000 is our input. That got multiplied to be negative 30,000. We added that to 155,000 to get 125,000. So that's our compare value. A compare value of 125,000 will generate this pulse, which will then drive it in this position. And then let's do our last case where it's a really negative number. So negative 26,000. Well, so yeah, multiplied it, added it, it got clamped. So that is that. So yeah, now let's make it go back to 0. So as you can clearly see, it is fully functional, and we have successfully implemented our PWM controller module and definitively proven that it is indeed working, that it can take in a number R of t and drive its position in a very linearized fashion. Alright, so that is how we designed the PWM portion of the PID controller. In the next video, we'll take everything we have built here, along with the circuitry from the previous video, and use it to implement the full proportional controller. If you're interested in getting the exact code used in this demonstration, along with the full source files for every video in this series, consider checking out the digital book in the description. It goes into far more detail than I can fit into YouTube videos, and it gives you all of the downloadable files so you can follow along directly on your FPGA. And also, if you're passionate about Verilog and want to see more advanced projects like this, supporting the book genuinely helps. It shows me that there's a real demand for this kind of content and lets me dedicate more of my time to making these tutorials. Anyway, that's all for now. If you enjoyed the video, feel free to leave a comment, like, and subscribe. Thanks for watching, and I'll see you in the next one.